I will say this though, because we all know surface mount and stencil manufacturing is going away. I was recently able to. I'm going to be doing DOE on different types of fluxes for through-hole, because through-hole is going to take over. It's coming back. And
Welcome to the Decode Podcast. We are joined by Gayle Towell. She's the technical marketing lead at AIM Solder. She holds a master's in math and physics from the University of Oregon, which happens to be producer Paul's alma mater. She's very recognizable as a speaker at many industry events. I recently spoke at an event where Gayle was speaking as well, and she gave a great talk on when to make the move to Type 5 paste. And she's going to be the proud recipient of the Next Gen Best Paper Award for her paper, Rethinking Area Ratio, a physics-based model for predicting solder paste transfer efficiency for thin stencils. So, Gayle, welcome. We're glad to have you here. How are you doing, and what are you doing?
Well, right now I'm sitting here on this podcast and very happy to be here. But what am I doing is a very big question. I mean, which subcategory should we launch into, and what kind of level of detail are you looking for? Maybe you should be more specific.
it's like a Jeopardy. It's like a Jeopardy page. I want to probe. But yeah, Gayle, I want to jump in first because I've had a really interesting week in the reflow oven. A lot of bowing. I had some really thick PCBs, heavy layer count, heavy grounds. So it's been me and the profiler a lot this week. And thankfully I was blessed with a good process engineer, many years experience in the business. And, you know, his claim to fame is about 10, 15 years ago, he was able to successfully run at 60 inches per minute on a 125 inch oven. Right. So he got that to flow great. And, so he could make my 34 inches per minute hum, So we were talking outside one day after we were having a issue at the oven, and I don't know why. And I know this in hindsight, this looks like basic 101, but let me back this up too from the user aspect. When we look at a data sheet on paste, for example, and I don't know what Ames is, but other ones that I've tried, they have like this crazy window of squeegee speed, right? It'd be like anywhere from 5 to 300, right? Like they don't give you like, hey, this works the best. And they'll say like reflow time, how long to put it in the oven for? They'll be like 3 to 5, somewhere around there, right? Like they don't tell you the sweet spot. So my PE was saying like, when you get paste, talk to the expert of that paste and say, where does this flux like to be activated at? Where does this flux like? And he kept talking about flux, and I go, why do you keep talking about the flux? He says, well, that's the secret sauce to every paste. And it kind of hit me because I'm like, well, I guess he's right, because for the most part the ingredients are all the same except for the flux in every paste. And I just never think about that before. So my question to you is when trying to figure that out inside of a reflow oven, where would you more like to put that into, the soak stage or the peak stage, to try to get it all out? Or is it just board dependent?
So yeah, I mean, the reason those sheets have such wide variety windows in them is because it really depends on the board, the substrate, the components, the thermal mass of what you're soldering, and all of that. So
the layer count, the density of the components.
Yeah, there's way too many variables. Like if you just go, I mean, there's so many variables that can affect the outcome, and you can kind of hone in on a few general things. And that's why it's always good to have a really experienced process engineer, because it's like they have that intuition that it should go like this. Right. And I think you have to build that up over a very large data set of experience. And so that kind of is the trick, is like the variables are just too many. One thing that so I've only been in the industry for like it'll be 3 years in April, and so my background before then was all physics, math, that land, and in that land you have a lot of very precise rules and laws, and this will work out this way when you're doing the theory side of it. And what I've noticed a lot is in the world of engineering, a lot of it is like, we just kind of feel our way through and approximate what might be occurring, and stuff starts working and we're happy. And in a way, at first I was like, well, couldn't you just go back to like first principles and like dial it in more precisely? And the reality is, no, you can't. There are too many variables to have that level of accuracy with like, here's this paste. It will work exactly like this in this situation. It's going to be different in every single situation. And so there has to be kind of this interplay between some understanding of the science and the physics principles behind how these things work, but also tweak and check and tweak and check and tweak and check until it starts to come out right, if that makes sense.
Yeah,
I don't
that
know if I
does.
really answered your question or just made new questions.
No, I mean
No.
it's because he told me like, well, the main thing and I take it from a user's perspective, right, is these paste companies don't want to be eliminated from a sale, when their paste could do that at that speed or at that process temp range. So it's more of like a brochure of, hey, this is our capabilities, not saying to,
Exactly.
and then
And what is going to be ideal is going to depend on the
yeah,
situation.
and talk to the
But
expert. But we can't figure this out with like the weight and size of the board and type of oven. You would think
It's
that
just
there's,
too nuanced. I mean, it's and that's the case up and down the processes of PCB assembly,
well,
right? I mean, I get questions all the time, stencil related, that people want an absolute figure. What transfer efficiency is this going to yield? Well, it depends, right? I mean, what's your screen printer? What's your squeegee speed, pressure? What's the board support look like, right? There's just so
exactly.
many
There's too
variables.
many variables. And one thing, I mean, you mentioned like you don't want your paste to be excluded from a trial or whatever. One thing we've noticed is when we can have one of our tech support engineers helping someone adopt a new product or try a new product, it's almost always more successful because you have someone with the years of experience and the know-how. And it isn't even just about our specific product. It's literally just they know which way to turn the dials. They know how to move that over there. They know that this problem will be resolved by this tweak. They see the specific situation. You don't get that same impact giving people an approximate suggestion over the phone or something like that. You
yeah.
physically being there and seeing all the little variables at play lets them make better optimizations to the process, basically.
I want the easy button where I can just put in these settings into my Kick profiler,
Just
probe it up.
call the tech support guy and be like, how does this work? And then they come and help you.
Well, even my PU was saying too is like this doesn't take into account your airspeed, for how much is blowing onto the in each zone, and it doesn't take into account like the actual CFMs coming out of the exhaust of your oven. Like there's, just that alone, one could, if you put your airspeed too high in the oven, then you're gonna dry out your paste before it even gets to where it needs to get to, right? So
Yeah, and every flux is a little bit different, and some of them will handle dry air better than others. Some of them, if you get a water-soluble flux and you have a humid work environment, you're gonna get soupy paste, and yeah, so a lot of it really, really varies a lot, and even it there's an interplay between I mean, you say you just have the metal powder and then you just have the flux could be all these different things, but there's an interplay between a flux chemistry and the powder, depending upon the alloy, depending upon the oxidation content of the powder before it's blended with the paste, depending upon the size of the powder, those actually come into play as well in determining the performance.
We certainly see that here. I'd love to say it's perfectly climate controlled in here. We never see any swing in any of our humidity or anything like that. But in Nebraska, it's pretty hard to control. And we've certainly seen some paste perform better than others in the radical swings, whether it's much more humid in the summer or when it's really dry in the winter. Some perform a lot better than others. And you see the exact same parameters on your screen printer, the same supports you've always had. Everything else is exactly the same, and suddenly it's not working the same, right?
Yeah, I mean, one of the things I get to do at AIM is try to quantify and answer some of the interesting questions like that by doing little studies. One of the things on my wish list to try to do at some point, though it's difficult to do this, is to run the same paste in the same conditions in different temperature and humidity environments for a direct comparison where everything else is held constant. What effect does that humidity level actually have? Is there a range? How big is that range before things start getting weird or problematic? And can adjustments be made to compensate for that and sort of quantify it a little bit better? We just know that in general, we like to keep the environment controlled, but to what extent do the deviations affect the process? And it'll be different with different paste types. I mean, a no clean is going to be very different versus a water soluble in a humid versus not humid situation.
So what does that experiment look like? Creating a microclimate around a screen printer and yeah.
Yeah, there lies the problem. I mean, they sell humidifiers and dehumidifier little machines, but I don't know how you make the bubble that controlled. So that's why it's kind of in my like fantasy land of this. Is there a way to do this at this point? Or
That would
maybe
be
you
super
just,
valuable though, because there's
yeah,
got to be some point where it's no big deal to up. It's a problem, right? It's
Yeah,
finding
there's a
that
trigger
line.
point. There's a fulcrum there for sure.
Yeah.
or a gradual worsening until it becomes critical.
Yeah. Yeah. You kind of mentioned something about variables and one of them being different alloy types, right? So obviously silver's been in the news a ton. I think as of today, it's somewhere around $85 an ounce. Um, you know, contract manufacturing in particular, there's pretty tight margins. So I have to imagine that assemblers are starting to look elsewhere, right? Let's kind of, we're scared to get away from SAC 305 because we trust it. You took lead free, took leaded solder from us, and now we love SAC 305, and now you want us to use something else. Well,
Exactly.
as people are being driven towards these different alloys, what are some concerns for like degrading performance, or are there some that work just as well, or
I'm
are
going to
you
try really hard not to make a sales pitch here. It's just
I
obviously
teed
that
you
a
up for one, I guess, huh?
Just go for it. Just go for it.
huge driver of a lot of our marketing focus this year is on this exact issue. So, I mean, SAC 305, that 3% silver, like if you just look at the cost of the metals that go into the alloy, even though it only contains 3% silver, that accounts for about 2/3 of the metal's price.
What?
So if you have silver, which like tripled in a year, that's a huge, huge difference. Yeah, it's huge. Well, silver's pricey. Silver is way more expensive than tin or copper.
Wow.
Yeah.
Right? And so even though it's 3%, it is the major price lever on that alloy. And so a lot of the ways people try to deal with that cost is they go for like low silver SAC. So maybe instead of SAC 305, we do SAC 105 or SAC 0307 or something like that. But then there's trade-off, right? So there's a reason SAC 305 was the one everyone liked when we went to lead-free, because the lower silver, you start to get some reliability trade-offs. It's not going to do as well with thermal cycling and things like that. So then the trick is, well, how do you lower the silver without, so that you can lower the cost without sacrificing the reliability? And this is where sort of those third generation lead free alloys come into play. When we start putting in an element like bismuth, bismuth wasn't in the original lead-free offerings because bismuth as an element doesn't always play well with lead. And when people were first moving to lead-free, there might be lead in components and still in parts of the process. But that's not an issue anymore. So now we can have an alloy that has a little bit of bismuth in it. And AIM makes an alloy called REL 61 that is SAC based. So it has about 1/5 the silver as SAC 305, and then it has a few percent bismuth in it. And that bismuth lowers the melting temperature just slightly and enhances the performance characteristics, gives it really good thermal aging and thermal cycling performance.
Isn't there a tipping point with bismuth where it helps in all of those characteristics up to a certain
Exactly.
percentage point and
That
then
is-
immediately like plummets off?
Well, it's not necessarily immediately, but I think studies show it's at about, I want to say about 6%. I think it tends to improve performance at 2 to 3%. And depending upon what other things you've added in, you can go a little higher than that. And then once you get past that, the brittleness of bismuth starts to cause other problems and you run into other issues. I actually wrote a paper a while back that kind of explains how bismuth is a performance enhancer in small percentages. And then it becomes, when it's the main constituent, like in a low temperature solder, then it's actually leading to issues like brittleness and other problems.
Becomes kind
You
of a
know,
high reliability concern at that point. But
Yeah. But when you're in that few percent range, it's improving the performance of the alloy.
yeah,
when we were
And
doing circuit board
yeah,
fab, the hotter level, the lead free, sometimes we'd have to add germanium to it. Do you know why that was? Like we would just send out the sample and they say, hey, add this, add these, and it looked like space rocks almost. That you just like weigh it out on a scale and then throw it into the tank and it
a little
dissolves.
germanium in there. I
Yeah,
don't remember off the top of my head exactly what germanium does. So it's usually when it's added to a solder, it's like trace amounts. And I'm blanking on
it was like
which
5
chemicals.
grams in like an 800-pound pot. You know what I'm
Yeah, it's
saying?
always
Like
like 0.003% or something tiny.
exactly.
Yeah, yeah.
Maybe it
Off
was
the
to
top of my head, I'm blanking
drop
on
the
what it
copper
does,
out
but
or
it does
something. I don't know.
something. It might be
Yeah.
that. It might be related to copper erosion because there's an alloy called SN100C, which
yeah.
is mostly tin, but has tiny bit of copper, tiny bit of nickel, tiny bit of germanium, usually used in wave solder because it has a higher melting point. And it was designed not only to have less, it's zero silver, so it's less expensive, but also to mitigate some of the copper erosion and sort of things that happen in wave soldering.
We use that in our selective. It works good.
Yeah.
That was the original one, and then their patent came up. I don't know what, about 5-10 years ago. Who knows how long ago?
Yeah, the
And then
patent is
everybody
expired.
cloned it.
Everyone's got some version of it.
Yeah.
So,
In
yeah.
fact, when the other suppliers like try to pitch it to me, they're always like, it's like SN100C equivalent. And I'm like, okay, like
Yeah,
it's
that's one thing we get to say that like we didn't invent it, but we had rights to produce it under the original patent when it
Mhm.
first came out. So we're like, we make the original
Right.
S100C. So
Well, you mentioned you've only been in the industry 3 years, right? So, I mean, if you don't know every single,
thing by now, I don't.
alloy and how it works and all that, I mean, I guess that ruins. I do have table 1.3 here from the solder paste technology principles and applications, and I was just going to rattle through some melting points of different alloys, but
I know a few.
we can do that on another
Or
one.
I can get close anyway.
If if it's 3 years and we talked to you a year ago at
S100C is
Apex,
227.
and it's about Apex time again. So if I do my math right, that feels like you were in the industry about 2 years when we talked to you last year. So
Nice. Sean,
thank
you've been
you.
doing a good
He's
job
really good
tutoring
with
Mr.
his
Thank you.
Stanfield.
action facts.
You know,
Really
I
good.
almost Sean dropped a really good post, an intelligent post today, and in that vein, I almost wanted to reverse roles and ask if germanium, like, why are you using flowers and solder paste? But I held back.
I am
You
so lost right now.
Those are flowers.
Okay.
After you've been in the industry only that, like, what did you know about solder paste before you entered the industry? Because you were already such an expert last year. So
Uh,
a quick
so,
study.
well, I mean, I was familiar with solder as a thing. My background again was math and physics. So, I mean, I had undergrad electronics class where we had solder wire and we were building little LED things that would tell you the weather or whatever we were making. So I wasn't unfamiliar with it as a concept and had played with it a little bit. I was not super familiar with the large scale electronics manufacturing industry and all of the processes therein. Um, but a lot of it was really easy to pick up because, again, it's a lot of basic physics, which, I mean, you talk about things have to melt and things go through phase changes and heat gets transferred at certain rates. And if something has greater thermal mass and what that means and how things can coalesce and what can happen at a metallurgical level. Like, so it's like there were places in my brain already ready for these ideas. And so I was able to pick up a lot of it very quickly. And when I first joined my company, they sent me to the applications lab for some training too. So I got like to hands on see equipment, see machines, see how the processes work, ask all the questions and all of that. And then reading and learning everything I can everywhere I go.
That's amazing. I would have thought you had like 10, 15 years in this minimum.
I just act like it and people
You
just go
do a
along with
great
it.
job. I'm telling
That's
you
the
right now.
secret.
I wouldn't even, I mean, like if you would have said, yeah, about 15, 20 years ago, like I
I'd be
wouldn't
like, that
even
sounds
bet.
right. That sounds
Yeah.
right.
How much? So
I'm
you
old
you do
enough
quite
for
a bit
that to
of
be my background.
you do quite a bit of speaking, Gail. How much do you think you've sapped up in terms of knowledge from kind of getting on the other side of the stage during these events that you speak at and absorbing the information that the other presenters are providing? Like, do you attribute that to a lot of your knowledge gain, or?
That's a lot of it. Yeah. So always feel like when I go to these conferences or events, it's just like massive in terms of how much I learn and understand because it isn't even just the little facts and details, it's context. It's understanding what topics are people talking about the most, what things are they concerned about, what things are they describing, and not even just on the conference and talk side, but show floor. Go to the equipment manufacturers. How does this machine work and what does it do? And you get the explanation, and then you're like, oh, like so the light bulbs start going off and then things that you didn't even have an awareness of you start picking up because now you're seeing them everywhere and you're it's like you don't know what you don't know and so you just start absorbing it all. And I've always been a big fan of I don't like to focus narrowly. I mean, we make solder, but solder is connecting the components. It's things to do with the boards. We have to know what's happening with the components. We have to understand how inspection works. So trying to understand everything around the solder and helps give more context to what we need the solder to do and why it's made the way it is. And so, yeah, I just feel like when I go to conference events, it's just massive thing. And my boss always makes fun of me because I write up a report of everything I learned and thought. And he's like, what are the 5 highlights? I don't want to read that. And I'm like, but it's all good. It's all
Yeah,
good.
yeah.
And then, yeah.
Too
Yeah,
funny.
it's so true.
And
There's so much that can be learned at those, and yeah.
And speaking of learning at the conferences, this is going to air probably after Apex, right? So you're getting the award um, for the paper, Next Gen. My brain cannot
Yeah,
handle that giant title that's in there.
I don't remember what it is either. So
Can you talk about what that paper is going to be about and what you actually discovered?
yeah, so one of the things when I first started learning all the solder stuff, I noticed we kept talking about how when printing with ultrafine paste or using thinner stencils, usually you have to use a slightly higher area ratio. But I couldn't ever figure out like there was no why. There was just it just is the thing. When it's the stencil is thinner and the paste is smaller, you just have to use a little bit bigger area ratio. No one knows why. Um, and so I started playing with trying to understand, like, well, why did we come up with area ratio in the first place? What is it telling us about what's happening with the solder paste, right? So it's basically describing the competition between two forces the force of adhesion when you're printing solder paste between the paste and the substrate, and the force of adhesion between the paste and the walls.
Mhm.
And so you got the ratio of those two areas. And when it's above a certain number, you're going to get good paste release. When it's below a certain number, you don't get good paste release, basically, right? And that limit is kind of determined experimentally because those forces of adhesion are going to depend on physical properties of the paste, whether the stencil is nano-coated and all of these other factors. But we still give this number of like 0.6 needs to be your minimum area ratio, just so people have an idea. And so I was thinking about that, and I was thinking about how those two forces that are being considered are both forces related that are going to scale with area, right? And there's also another force at play here that we haven't even included. If you do a force diagram from physics, intro physics, you got your solder paste. It's going to have a force trying to make it stick to the board. It's going to have forces trying to make it stick to the walls, but it's also going to have the force of gravity on it. And at first I was like, but it's tiny. That's going to be small, right? But then think about it. If you were to try to stencil print upside down and pull the stencil off, would you expect slightly different results than if you would? Because that force of gravity is doing something.
Have you done that
Okay.
DOE yet?
It's coming, right? So what I this is this whole thing here. Yeah. But the force of gravity depends on the volume of the paste, right? And so when you start getting thinner and thinner and thinner stencils, you've got those two forces, the area forces that are scaling with area, and you have gravity, which is scaling with volume. Those scale differently. And so you're going to get a deviation. So initially, when we were just using area ratio, factoring in gravity didn't matter because it was kind of absorbed into the fudginess of the other factors involved, right? And we assume all the stencils are roughly similar thickness. You're not going to see an effect from that.
They're probably all made with the same quality, regardless of your supplier.
Yeah. So if it's the same thickness, you're going to have similar sized deposits. But once you start getting thin, now you're laughing at me.
No,
we're
I'm laughing
that
at
was a dig at Elias.
I'm
That
laughing
was
at
a dig at
Elias's
Elias.
face. I
Okay,
only said that as
That was
a dig at him.
Elias. Yeah.
Okay, good.
We're always only laughing at Elias.
But anyway, so scales differently, so you get a deviation, which is why area ratio limit kind of changes. And then what I did was I took existing papers that had data where they had 2 to 3 different stencil thicknesses across similar area ratios, and they had print transfer data to show quite explicitly that, yeah, when you look at print transfer efficiency across the same area ratios, it's worse with thinner stencils. And so, and then applied a little math model based on if we include gravity, what should change, and showed that it kind of lines up with that.
Wow.
But that's kind of like the preliminary idea.
Is that the same
now we
type
have a
of
model.
paste used across all the different foil thicknesses?
Yeah, so I was pulling stuff from existing published papers, so I'm kind of limited with what I had there. And so this was just the start of the building of the model. And the general idea is that now there's like a rough model that will show you if your area ratio limit is 0.6 when the stencil is 4 mils, then it will have to increase to like 0.8 when the stencil is 2 mils or whatever.
Wow.
To actually get those precise numbers, we need to do a controlled study across a whole lot of stencil thicknesses with the same area ratio. So that'll be the next phase of things we're going to be working on. But that's what this paper is about, was just introducing that model and showing that it could work.
You know what's really cool, Gayle? One day they could pull this paper up to when they're on Mars and they're like, why isn't this paste releasing like normal? You know,
And
like,
they'll be
it's
like,
the
"But the force
gravity
of
change,
gravity is
right?
different here."
Yeah.
That's...
Pull up the towel effect, right? Like just kind of it's that's cool. Because Elias, does your software because I know when you're creating your stencil, you're always able to tell me what the AR is, in theory is supposed to be and what the T is supposed to be on each pad, right? That's strapping.
Area ratio for sure. Transfer efficiency, not so much. I mean, area ratio is predictive of transfer efficiency.
But does it take into account the stencil thickness, like Gayle's saying?
No.
In terms of like
AR?
its design rules, if it's going to, kind of pass or fail. I mean, it takes into account the thickness in terms of you need the thickness in order to calculate the area ratio.
Area of the surface. Yeah.
But yeah, if you were gonna kind of slide what was acceptable in terms of area ratio, that would have to be a decision that you made on your own end, and you could change those parameters. But no, there's no automatic kind of correction for thickness in terms of, okay, it's a thinner foil, so we need to go to a larger. And
give me another year or two.
Yeah, no, and this is super interesting. I can say, anecdotally, I've experienced, end users printing very thin, down to 40 microns, with some fairly challenging area ratios and having good results. But I think it is interesting because I almost look at the gravity thing as, okay, we're looking at area ratio, which is mainly XY. Sure, you have the Z of the aperture wall thickness, right? But
Mhm.
if that Z extends up, right, that's kind of the force of gravity. So I'm just trying to think about it in another dimension. Maybe it's not a fantastic example, but I think about we talk about, you know, the 5-ball rule or the 7-ball rule or whatever you want to
These
subscribe
are
to.
rules. They're like
Right. The guidelines
guidelines because
ish,
everything's a little
right?
different. Yeah.
But kind of along that same vein of thinking, as we talk about thinner foils, you've got to start thinking about the solder balls in the Z, right? So if you're using a 2 mil stencil and trying to print 3 mil, you can't even stack two spheres on top of each other, right? If you're using type 3 paste rather. So yeah, I think thinner stencil foils introduce a lot of things that we haven't necessarily thought about before and need to start thinking about. So this is really interesting work that you're doing, and I'll be waiting with bated breath to see the results.
Yeah. Yeah,
When
it's
you
fun. I like working on projects like that where I'm basically going back to fundamental principles, like where my happy place where there aren't too many variables messing everything up and making the math ugly and intractable. So, and I think that's like what a lot of the a lot of the IPC guidelines and things like that, they're kind of built on a general model of how the physics works. But that, like I said, we have that 0.6 area ratio limit, but if you are using different pastes, you're going to get different results. If you are using different stencil finishes, you're going to get different results. If you have a different substrate, you might get different results. Like, so it's not, nothing is really, there aren't really hard and fast rules because it always depends on the specific situation you're dealing with.
And I think that's why, 75-25 is specifically listed as a guideline rather than a
Mhm.
standard, right? I think that's an important distinction.
And yet you'll have plenty of customers who are like, well, why isn't it meeting the standard that is specified over here? And it's like, but it works. So we're fine, guys. We're fine.
eventually Big Stencil will have to come up with a real standard that we can hold them to, and they can't hide behind this guideline
It'll be a really
business.
fancy
forever.
algorithm where you input like every last detail of the paste and the specifics of what was the viscosity measurement when it came in and what is the like surface smoothness of your substrate. And then it will tell you the answer.
Big stencil. I love that, Daniel. That's awesome.
Yeah, well, once you stop supporting your boards with toothpicks, we'll talk.
Gayle, I worked at Kawasaki back in the day, and they used to have this like little 2-lane tiny little stretch of road that they would take the ATVs and dirt bikes and stuff and do a little stress test on them. So when you guys are developing a new paste, do you ever give it to somebody like Sean to do stress testing by putting it through his normal assembly process?
I mean, we could start incorporating that. Um, no, that's not usually how our test protocol works. We're all like more refined than that, right? We have our very specific tests that we do in our applications lab with the print tests, but we do. And I heard you talking about this in the Chris Shea podcast I was just listening to for this, right? We design things to fail, right? So we do a lot of okay, we have our own sort of test boards that we've designed where you've got different zones where things get progressively worse until something is going to fail for sure, and to seeing where does that failure occur. But sometimes we will give assemblies and things to a university lab or other places to do drop shock tests, much more controlled than driving the Kawasaki down the road. It's, we drop it from this height and it has this much force applied to it and this level of acceleration, this impulse over so many times, and then we see when it breaks.
I'm still trying to figure out if that was an insult towards me or not. Because I would enjoy a dirt bike ride with a brand new Kawasaki, right? Like that sounds awesome. So,
Yeah, I don't think that's what Daniel was suggesting.
okay,
but
well, it was an insult then. I'm just trying to figure out if I should
probably.
should I be
Your
offended right
assembly
now or what?
practices would be enough to cause a breakage in to stress test these solder's capabilities.
I will tell you this: a company uses me for SIR testing samples, and part of me,
SIR testing?
yeah, I like to call it SIR. And part of me wonders if they're giving it to me because they think I'm clean or if they think I'm a dirty shop. So like, do they want best case scenario or worst case scenario? And then they're just like, give
They
it to
know,
me.
like,
Right?
if
You
it
know what
gets
I'm
through
saying?
yours, they've got all bases
That's
covered.
what I'm like. Are they going through me because of that? Or are they going through me because of I painted the walls and got new floors and
Reality is they're ticking a box. Was the test done? It was done. Did it pass? Yes. Good.
all right.
No, you're special, Sean. And
All
listen,
right.
look at me. Look at me. You're special. Don't
Do you
listen to
actually
Gayle, okay? Don't listen
do
to
you
Thank you.
actually do you actually perform the cleaning? So you assemble the
I'm not allowed to do that part.
okay. So interesting.
Yeah. I do wear gloves during it, and everybody handling it wears gloves. So I try to keep it, as uncontaminated as possible, right? So, because I feel like they're trying to set me up somehow. I'm like, they want me to be dirty, but I'm not going to be dirty, right? I want a low number coming in. I don't know. I'm getting it. I'm way overthinking it, like most of
Yeah, I mean, because SIR is going to be more valuable for qualifying the cleaning process than the assembly process. I mean, I guess the two definitely are tied in, right? If you've got some bad practices
Yeah.
on your SMT line, then
I will say this though, because we all know surface mount and stencil manufacturing is going away. I was recently able to. I'm going to be doing
What do
DOE
you
on
mean?
different types of fluxes for through hole, because through hole's going to take over. It's coming back,
Yeah.
are we
and
it's kind of like
Okay.
bell bottoms. They're
I'm
back.
bringing it
What's old
back,
is
baby.
new.
Yeah,
That's why
Okay.
none of us were catching what you were saying. But okay, thanks
2030.
for clarifying.
Really?
Go
2030.
on. Go on.
We're going back to through hole. But I was recently able to try I believe it's the FX16, if I have that number correct. Super happy with the results. In fact, like I had to stop my operator from loading it into all of the machines. I was like, wait, we're doing a study, so let's one thing just one at a time, right? So but it was interesting to see how much, it's just amazing how much a flux can affect your selective solder. But I have this issue, and it's not just with it's every flux I have tried, right? Where I get these little solder balls randomly onto the board. Do you know what causes that? And Danny, you back bam on this. You know what I'm saying about these?
I've never seen one ever.
Okay, I probably have 4,000 pictures from him.
Our test boards deliberately make them happen in places. So,
No,
this
yeah,
is
I
with
know what you're talking
selective. You're saying, or
Yeah,
is this
selective. Yep.
okay? I'm less familiar with some of the causes in selective. Much more familiar with what makes them happen in SMT. So, off the top of my head, I don't think I can answer. Other than it could be
Describe
many things. There are
describe it.
many variables at play.
Like, go
Try to
ahead into the
separate off.
specifics of what it is on the SMT side, and Sean and I will tell you what the corollary is.
So you can get those solder balls if you've got too much paste and then it kind of coalesces in one spot. It could be an issue with if the paste isn't good in terms of past its expiration date or wasn't too much oxidation. And you can end up with getting those solder balls formed. Too much paste can make it happen, especially like mid-chip solder balls will often happen for that reason. And you can use like a home plate print design to kind of minimize that effect. So a lot of times it's a paste volume issue, but it can also be a paste quality issue. And then sometimes you can improve things with adjusting the reflow profile a little bit, depending on what the build is.
I have a question for you, Sean. Have you noticed it as much? You've got a newer machine recently, right? Has it been the same since you got a new machine? Because your new machine actually has preheat, right?
It's so tough to answer that. So Mike Conrad's going to kill me when I say this out
I'm just
loud.
guessing. Like my understanding was that it was because you have, if you've got it, the flux is rapidly introduced to. I mean, if it isn't brought up to a hot enough temperature, and then you introduce it to that, 300-degree solder flowing on it, that it can cause like the little.
Well, that would follow kind of the
explosion,
same.
little pop.
That would follow basically the same principles of surface mount, right? If
Little
you
splatter.
if you're bringing the ramp up too fast, then you're going to get that splatter, and yeah. So answer the question, Sean.
Like I said, Mike Conrad's going to kill me for saying this. So, Mike, if you're listening, just mute it for about the rest of the show. Just turn it off. I had so much rework previously from the not having the preheaters installed on the selective solder and the heater, the topside heater as well.
Right.
I don't know a board that wasn't like scrubbed with isopropyl first, and or like immediately just thrown into the parts washer, right?
Mm-hmm.
And with the new one and with these new fluxes that we're using, there is zero residue compared to my old flux, right? So now we get the boards done, right? And there's nothing to touch up, and there's no residue. So like, it doesn't look like if the customer doesn't want it to wash, I'm not going to wash it. And then we look under the scope now, right? So this is what we're looking for now, where before it was going to get taken off by one of those other processes. So I can't tell you what it was like before because we didn't even look under the scope because we were scrubbing it or sending it through, the Trident to wash off. So we just started noticing it now because we're not cleaning it, and now we're seeing what's going on, right? So I hope that answered your question. I don't know if it did. Basically, I don't know. How about that?
I mean, there were certainly words in there.
Yeah.
I try. I mean, I don't know. I'm just being honest, right? Like before we had it just without top and bottom preheat, man, and then topside heater while you're soldering. It was such a different type of soldering experience than what I'm experiencing now with the new selective solder that has all that in there. And it's also like a brand new machine and new solder pot, so everything's tip top, right? Compared to a 6-year-old selective solder and a 4-year-old selective solder. So I don't know. The best answer I've heard so far was that there's got to be a reason why that ball of solder doesn't want to go to that pad on that through hole, and why does it want to stick to the actual mask, right?
Mm-hmm.
So if you can
So
find out
somehow the metal isn't wanting to touch the other metal and suck it in to place where it's supposed to go, like
exactly.
that
So we've
individuality,
we
some
try
of
to
them
mess
just want to be
around.
different.
It wants to be its own metal.
Yeah.
We try to mess around with like the heat to try to lower it. Maybe we're getting too hot, and then we try to, all right, well, let's go hotter. And then, I didn't want to go too long because I still have to like ship product out of my shop. So we just kind of accepted it is what it is, and we're just gonna have to look under the scope now. So
could it be like a contact time with the
solder? There's, like you said in the earlier part, unfortunately, there's variables, right? So
yes, there's so many.
Yes, there's so many.
Tweak this one,
and then like what would work on this 4-layer board, right? With this PCB design might not work on another 4-layer board with a completely different PCB design, right? And
I've always thought it would be fun to give a talk on like just the combinatorics of it depends, and just show from a mathematical perspective, like when you start adding all of these variables, like the actual result of the number of combinations of things that you could be looking
Doug
at.
Pauls have a trademark on that though?
Yes.
What would be the lesser?
We'll have to like quote him in there, but
what would be the better odds, figuring that out or actually winning the lottery, right? Like, which is right?
Did you find the right combination, or should you buy a lottery ticket and hope for that instead?
Well, Gayle, we definitely all enjoyed this, and thank you very much for your time. Once again, can you tell the audience how they can find you on social medias and plug whatever you need to for AIM?
Well, I'm on LinkedIn, so you can find me there, just under my name. There aren't too many Gayle Towells in the world, so I'm usually pretty easy to find. If you ever want to email me about any solder questions or want me to forward you on to a technical engineer, my email is gtowell@aimsolder.com. And I will be at Apex. Come find me. Come talk to me. I love to learn things, meet people, and come up with fun new projects to engage in. So.
Well, thanks to you again, and thank you to the audience for sticking with us through Rev 3. We appreciate everyone for following. Like and hit subscribe, and see you next time.